Children, when you enter in a dark room, why you are not able to see anything? What else we need to see different things? Yes, the answer is light. In previous classes, we have learned that an object reflects light that falls on it. That reflected light, when enters in our eyes, enables us to see different things. In this part of chapter, we are going to learn something more about reflection, spherical mirrors, image formed by spherical mirrors, uses of spherical mirrors, and a sign convention for reflection by spherical mirrors. We are going to discuss all these topics in detail. But before this, it is necessary to learn to understand some important terms. So, let's have a look. What is light? Light is a form of energy which produces the sensation of sight in us. Ray of light. The path travelled by light is represented by a straight line. One such line is known as ray of light. Beam of light. Group of light rays travelling together is called a beam of light. Incident ray. Any ray which falls on the reflecting surface is known as incident ray. Reflected ray. Any ray which is reflected back by the reflecting surface is known as reflected ray. Children, now let's start our chapter with reflection of light. Children, you might have observed that when light falls on any surface like wall, mirror or any polished surface, then it returns back in the same medium. This process of sending back the light rays which falls on any shining surface is called reflection of light. There are two laws of reflection of light which we have learned in previous classes. According to first law, the angle of incidence is always equal to the angle of reflection. Means angle I is equals to angle R. According to second law, the incident ray, the normal at the point of incidence and the reflected ray all lie in the same plane. These laws of reflection are applicable to all types of reflecting surfaces including spherical mirrors. Children, you see yourself every day in the mirror. That mirror is a plane mirror. The image formed in mirror is always erect, equal to the size of the object and is virtual in nature. Here, virtual means? Children, virtual means that image cannot be obtained on screen. So, image formed by the plane mirror is a virtual image. Now, let's discuss about spherical mirrors. Spherical mirror is that mirror whose reflecting surface is the part of a hollow sphere of glass. The spherical mirrors are of two types, convex mirrors and concave mirrors. Let's understand them with the help of an activity. Children, take a big shining steel spoon. Its inward surface acts as concave mirror, whereas its back bulging surface acts as convex mirror. Now, take a pen in front of its bulging outward surface which acts as convex mirror. You will see that the image formed here is erect, virtual and smaller than the object. Again, I used term virtual because we cannot obtain this image on screen. Now, take this pen near or far from the spoon. You will see that the image is always erect, virtual and is small in size. Now, turn the spoon and see the pen in its inner bent-in surface which act as concave mirror. You will see that the image formed here is inverted and smaller in size. When you take the pen far from the spoon, the image formed is smaller and inverted in nature. But when you take the pen near to the spoon, you will see that the image now formed is bigger in size. Now, let's see how concave mirror converges the light rays falling on it. For this, we need a concave mirror and a paper. Hold the concave mirror and direct its reflecting surface towards the sun. Direct the light reflected by the mirror onto a sheet of paper and move it back and forth gradually until you find a bright, sharp spot of light on paper. Actually, this spot of light is the image of the sun on the sheet of paper. This point is the focus of the concave mirror. You will observe that the paper starts burning due to light rays of the sun. Now, let's see some important terms related to spherical mirrors. A spherical mirror whose reflecting surface is curved inwards, that is, faces towards the center of the sphere, is called a concave mirror. Whereas, the spherical mirror whose reflecting surface is curved outwards is called a convex mirror. The center of the reflecting surface of a spherical mirror is called the pole. It is usually represented by the letter P. The reflecting surface of a spherical mirror forms a part of a sphere. This sphere has a center and it is called the center of curvature of the mirror. It is represented by the letter C. The radius of a sphere of which the reflecting surface of a spherical mirror forms a part is called radius of curvature of the mirror. It is the distance between P and C. It is represented by letter R. An imaginary straight line passing through the pole and the center of curvature of a spherical mirror is called the principal axis. The principal focus of a concave mirror is a point on its principal axis to which all the light rays which are parallel and close to the axis converge after reflection from the concave mirror. Whereas the principal focus of a convex mirror is a point on principal axis from which a beam of light rays initially parallel to the axis appears to diverge after being reflected from the convex mirror. The distance between the pole and the principal focus of a spherical mirror is called the focal length. It is represented by letter small f. There is a relationship between the radius of curvature, that is r, and focal length, that is small f, of a spherical mirror. Radius of curvature of a spherical mirror is found to be equal to twice the focal length, that is R is equals to 2F. Now children, let's see image formation by spherical mirrors. We can study the formation of images by spherical mirrors by drawing ray diagrams. To construct the ray diagrams, in order to locate the image of an object, an arbitrarily large number of rays emanating from a point could be considered. However, it is more convenient to consider only 2 rays for the sake of clarity of the ray diagram. The intersection of at least 2 reflected rays give the position of image of the object. For example, a ray parallel to the principal axis after reflection will pass through the principal focus in case of concave mirror, or appear to diverge from the principal focus in case of a convex mirror. A ray passing through the principal focus of a concave mirror or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. A ray passing the center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. And a ray incident obliquely to the principal axis towards a point P on the concave mirror or a convex mirror is reflected obliquely. By using any of these 2 rays, we can make ray diagrams easily. Dear children, now let's see image formation by convex mirrors. First of all, when object is placed at infinity, imagine the light rays fall on the mirror parallel to the principal axis, and after reflection, the reflected rays appear to emerge from point F, that is principal focus. We can see that here the image is formed at focus F. It is virtual and erect and very small in size. For second position, we place object between infinity and pole of the mirror. Imagine one incident ray comes parallel to principal axis, and after reflection it appears to emerge from principal focus. Second incident ray passes through C and reflected back on the same path. Both the rays intersect each other at point A dash. By joining the line A dash B dash, we obtain image A dash B dash. This image is formed between P and F and is virtual, erect and diminished in size. Dear children, let's try to form image by a convex mirror. Here for this activity, we have a convex mirror on mirror stand, a candle which act as an object, and the screen for obtaining the image. Here we will try to obtain the image of the candle on the screen with the help of a convex mirror. So let's try. Here I have kept this candle between the mirror, convex mirror, and the screen. You will see that for any position of the candle, we are not able to obtain any image of this candle on the screen. It means when we are not able to obtain the image on screen, the image is virtual, because virtual images are not being obtained on screen. So, where the image of this candle should be obtained? In mirror? Let's try. Now you are able to see that a small, erect and virtual image is here in this mirror. Why I have said virtual? Because we are not able to obtain this image on screen. It is here in the mirror and it is smaller in size, virtual and direct. For any position of the candle, you can see that the image of the candle is in the mirror is virtual and erect and smaller in size. So here we have seen that convex mirror always forms a virtual and erect image of an object which is always smaller than the object. Now let's see uses of convex mirror. Convex mirrors are commonly used as rear view mirrors in vehicles because they always give an erect and diminished image. Convex mirrors gives a wider field of view as they are curved outwards. Thus, convex mirrors enables the driver to view much larger area. Dear children, now let's understand image formation by concave mirrors. For this, we use this table. Here you can see that for 6 different positions of the object, we obtain different positions of the image. First of all, when we place object at infinity, then image is formed on principal focus F, which is highly diminished, means small in size, and real and inverted. Now, why real here? Because we can obtain this image on screen. You will observe that as we take object near to the mirror, the image formed far from the mirror. For second position, we place object beyond C, then the image formed between principal focus F and C, and it is diminished in size and real and inverted. Now, when we place object at C, the image also forms on C, which is now of the same size as the object and real inverted in nature. For fourth position, object is being placed between C and F and the image is now formed beyond C. It is now enlarged, real and inverted in nature. Next, as the object is placed at F, the image formed at infinity. And now it is highly enlarged, real and inverted in nature. Now for last position, when object is placed between F and P, the image is now formed behind the mirror, very enlarged and virtual and erect in nature. Virtual because now we cannot obtain this image on the screen. Dear children, let's try to form images by concave mirror. For this activity, to show the image formation with the help of a concave mirror, and we need a concave mirror here in the mirror stand, a candle as an object and a screen to obtain image. Now we are going to place the candle between the mirror and the screen. Now you will see that an image is formed on screen. Look here. As we move this candle far from the mirror, you will see a very sharp image is present on the screen of this candle. And look here, the image of this candle is inverted in nature, and as we are able to obtain this on screen, this is a real image which is inverted and smaller than the size of the object. It is smaller than the size of the flame of this object. So, as we will move towards the mirror, you will see that the image on the screen is going to be blurred. It is now increasing in size, and slowly as we reach near to the mirror, you will see that the image on the screen is slowly going vanished. Now we are not able to see any image on the screen. This is the position which is, we can say, the object is placed between F and P. For this condition, concave mirror form a virtual and enlarged image, which is virtual and erect. Because we are not able to see this position on the screen. That is why this image is here virtual and erect. So here we have seen different images formed by concave mirror for different position of an object. Dear children, now let's see some uses of concave mirrors. Concave mirrors are commonly used in torches, searchlights and in vehicle headlights to get a powerful parallel beams of light. They are often used as shaving mirrors to see a larger image of the face. The dentists use the concave mirrors to see large images of the tooth of the patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. Now, let's learn sign convention for reflection by spherical mirrors. While dealing with the reflection of light by a spherical mirror, we should follow a set of sign conventions called the New Cartesian sign convention. According to this, the object is always placed to the left of the mirror. It means that the light from the object falls on the mirror from the left hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin are taken as positive, and those measured to the left of the origin are taken as negative. Distance measured perpendicular to and above the principal axis are taken as positive, whereas distances measured perpendicular to and below the principal axis are taken as negative. Now let's see mirror formula. In a spherical mirror, the distance of the object from its pole is called the object distance. It is represented as small u. The distance of the image from the pole of the mirror is called the image distance, and it is represented as small v. The distance of the principal focus from the pole is called the focal length, which is represented by small f. The relationship between these three quantities is given by mirror formula, which is expressed as 1 by v plus 1 by u is equals to 1 by f. While using this formula, we all must use New Cartesian sign convention. According to this, the distance of object u is always taken as negative for convex and concave mirrors, because object is always present at left hand side and the distance to left hand sides are taken as negative. As the object is always placed on principal axis, the object height is always taken as positive for convex and concave mirrors. Focal length small f is in positive for convex mirror and negative for concave mirrors. Image distance V is in positive for convex mirrors and is negative for concave mirrors till the object isn't placed between F and P. Images formed by convex mirrors are always virtual and erect in nature, whereas images formed by concave mirrors are real and inverted, except the one situation where we place the object between F and P. Now let's understand magnification. Magnification produced by a spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. It is expressed as the ratio of the height of the image to the height of the object. It is represented by letter small m. M is equals to height of the image, that is h dash, by height of the object, that is small h. M is equals to h dash by h. It is also related to the object distance u and image distance v as m is equals to minus v by u, or we can write m is equals to h dash by h is equals to minus v by u. A negative sign in the value of magnification indicates the image is real, whereas a positive sign is in the value of the magnification indicates that the image is virtual. So dear children, now let us see what we have learnt in this chapter. The process of sending back the light rays which falls on the surface of an object is called reflection. Mirrors and lenses form images. Images can be either real or virtual depending on the position of the object. Spherical mirrors are of two types, convex mirror and concave mirror. Mirror formula 1 by V plus 1 by U is equals to 1 by F gives the relationship between the object distance U, image distance V and focal length F of a spherical mirror. The focal length of a spherical mirror is equal to half its radius of curvature. Dear children, now let's discuss some questions and I hope that you know the answers. Question number 1. If the image formed by a concave mirror is observed to be virtual, erect and larger than the object, where should be the position of the object? Yes, in case of concave mirror, when we obtain a large erect image, it means the position of the object is between the pole of the mirror and its principal focus, means between P and F. What type of images are formed by convex mirror? Yes, convex mirror always form small, virtual and erect images. If your image always appears erect, no matter how far you stand from the mirror, which kind of mirror is it? Yes, exactly right. That mirror is a plane mirror. What will be the focal length of the mirror whose radius of curvature is 30 centimeter? As we all know that radius of curvature is equals to 2f. For f, the formula will be small f is equals to r by 2. R is 30 centimeter here. So 30 by 2 is equals to 15 centimeter. So the focal length of that mirror is 15 centimeters. Children, now I have a question for you to do in your notebooks. Do read your chapter thoroughly, understand it, and then do it right in your notebook. The question is, draw ray diagrams for the image formed by concave mirrors. So, you have to draw all these 6 ray diagrams for all these 6 positions. One of this chapter, we have studied that light travelled in a straight line. We have studied how spherical mirrors form images, why convex mirrors are used as rear view mirrors in vehicles. What is the sign convention for the mirrors? Now, in this part of the chapter, we are going to discuss about refraction of light, refraction through a rectangular glass slab, refraction through spherical lenses and image formation by spherical lenses, laws of refraction, refractive index, and sign convention by spherical lenses, and power of lens. We are going to discuss all these topics in detail. So, let us start with refraction of light. Children, have you ever noticed path of light? What happens when light enters from one transparent medium to another? Does it still move along a straight line path or change its direction? Let's understand it with some examples. Take a pencil and keep it in a glass of water. The light reaching you from the portion of the pencil inside water seems to come from a different direction compared to the part above the water. Similarly, a pond of water appears to be less deep than it actually is. A coin placed under water in a glass appears to be raised. When a thick glass slab is placed over some printed material, the letters appear raised when viewed from the top. Why all this happen? Let's look the first case. When a pencil is partially immersed in water and held obliquely to the surface, it appears to be bent at the point where it enters water. Actually, light comes from different directions, enter our eyes, and that is why pencil appears to be bent. All these examples shows that light does not travel in the same direction in all mediums. It appears that when travelling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomena is called refraction of light. Let's take one more example. When we place a coin in a beaker filled with water, the coin appears slightly raised above its actual position. Light coming from the coin first travels in water and then travels through air and reaches our eyes. Here, due to refraction, it appears raised. Dear children, now let's understand refraction through a rectangular glass slab. For this, fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle and draw its outline. Let us name the outline A, B, C, D. Take 4 identical pins. Fix 2 pins, say E and F, vertically such that the line joining the pins is inclined to the edges, AB. Look for the images of the pins E and F through the opposite edge. Fix two other pins, say G and H, such that these pins and the images of E and F lie on a straight line. Remove the pins and the slab. Join the positions of tip of the pins E and F and produce the line up to AB. Let EF meet AB at O. Similarly, join the positions of tip of the pins G and H and produce it up to the edge CD. Let GH meet CD at O dash. Join O and O dash. Children, you will notice that the light ray has changed its direction at points O and O dash. Note that both these points O and O dash lie on surfaces separating two transparent medias. The light ray at point O has entered from a rarer medium, that is air, to a denser medium, that is glass. And the light ray has bent towards normal. At O dash, the light ray has entered from glass to air, that is from a denser medium to a rarer medium. The light ray here has bent away from the normal. Children, here EO is the incident ray, OO dash is the refracted ray, and O dash H is the emergent ray. You may observe that the emergent ray is parallel to the direction of the incident ray. Why does it happen so? The extent of bending of the ray of light at the opposite parallel faces AB and CD of the rectangular glass slab is equal and opposite. That is why the ray emerges parallel to the incident ray. So, dear children, refraction is due to change in the speed of the light as it enters from one transparent medium to another. As we know that light travels in a straight line if travels in the same medium. But the speed of light is higher in a rarer medium than a denser medium. Thus, a ray of light travelling from a rarer medium to a denser medium slows down and bends towards normal. When it travels from a denser medium to rarer medium, it speeds up and bends away from the normal. Dear children, now let's understand laws of refraction. Refraction of light on going from one medium to another takes place according to two laws of refraction. According to first law, the incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. And according to second law, the ratio of sine of angle of incidence to the sine of angle of refraction is constant for a given pair of media. It is also known as Snell's law of refraction, that is sin I by sin R is equals to constant. This constant is called the refractive index of the second medium with respect to the first. Let's understand refractive index in detail. The extent of the change in the direction that takes place in a given pair of media is expressed in terms of refractive index. We have learnt that light travels with different speeds in different media. light travels fastest in vacuum with speed of 3 into 10 raised to the power 8 meter per second. The value of the refractive index for a given pair of media depends upon the speed of light in two media. If medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to vacuum. This is called the absolute refractive index or only refractive index. It is represented as N. If c is the speed of light in air and v is the speed of light in the medium, then the refractive index of the medium Nm is equals to speed of light in air by speed of light in the medium. Nm is equals to c by v. Children, the refractive index of water is 1.33. This means that the ratio of the speed of light in the air and the speed of light in water is equal to 1.33. Dear children, now let's learn refraction by spherical lenses. You might have seen watchmakers use a small magnifying glass to see tiny parts, and people using spectacles for reading. The glasses used in spectacles and that by a watchmaker are examples of lenses. Children, a transparent material bounded by two surfaces of which one or both surfaces are spherical forms a lens. The lenses are of two types, convex lens and concave lens. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens or convex lens. It is thicker at the middle as compared to the edges. Convex lens converges light rays, hence are called converging lenses, whereas concave lens is bounded by two spherical surfaces curved outwards. It is thicker at edges than at the middle. Such lenses diverge light rays and are called diverging lenses. Children, lenses also have center of curvature and principal focus as in mirrors. The central point of a lens is called its optical center. The principal focus of a convex lens is a point on principal axis to which light rays parallel to the principal axis converges after passing through the lens, whereas the principal focus of a concave lens is a point on its principal axis from which light rays originally parallel to the axis appear to diverge after passing through the concave lens. A lens has two foci. The two foci of lens are at equal distances from the optical center, one on either side of the lens. The distance of principal focus from the optical center of a lens is called its focal length and it is represented by small f. Now let's see image formation by lenses. First, we will take convex lens. Place a lighted candle in front of a convex lens and a screen on other side of it. Lighted candle should be placed far from the focal length of the lens, say at infinity. You will see that a sharp, clear image of the candle appears on the screen. The image is real and inverted in nature. Now, why real? Because we are seeing the image on the screen, and the images which cannot be obtained on screen are called virtual images, and which can be obtained on screen are called real images. Now, take the candle from infinity near to the lens at different positions, like at 2f1, beyond 2f1, between f1 and 2f1, and observe the images on screen. You are seeing that in all situations, the image formed will be real and inverted. But as you bring the candle near the lens, size of image increases gradually. For last condition, when we place candle between focus and optical center, the image increases in size, and now we cannot see it on screen. Now the image is positioned on the same side of the lens as the object and is enlarged, virtual and direct. In this way, with the help of this table, we can find nature, position and relative size of the image formed by a convex lens for various positions of the object. Let's do it. For the image formation by convex lens, I have here a convex lens, in the lens stand, a screen and a candle which act as an object here. Now, as you are seeing, I have placed this lens between the candle and the screen, and there is a bright part on the screen. This bright part is the image of this candle. Now, as we take the candle far away from the lens, as you can say at infinity, you observe a very sharp image of this candle. This is the image of the candle, which is inverted, very small and real. Now, why I have said real here? Because we are able to obtain the image of the candle on the screen, and the images which can be obtained on the screen are called real images. Now, as we take the candle near to the lens, the size of the image increases gradually, but still it is inverted. Now, the size is increasing regularly. Now, as we place the candle very near to the lens, as we can say between the optical center and focus of the lens, here on the screen there is no image of the candle, and you can see the image of the candle in the lens. Now it is bigger in size and virtual and direct. Why I have said virtual here? Because in this situation we are not able to obtain the image of the candle on the screen. So, in this way we obtain different images of this object by placing it at different positions from the lens. Dear children, now let's see image formation by concave lens. Children, when an object is placed in front of a concave lens, it forms a diminished or small, virtual and erect image irrespective of the position of the object. Let's observe it by doing. To obtain the image from the concave lens, I have a concave lens in the lens stand, a screen and a candle which act as an object. Now children, just look at the candle and the screen. I am placing the candle near the lens and far from the lens, but in any situation there is no image formed on the screen. You just see that the image of the candle is there in the lens, and here it is very small, virtual and direct. Irrespective of the place, anywhere I place the candle, you will see the image of this candle in this lens and not on the screen. It means the concave lens forms erect and virtual image of an object. It is very small in size. These are called virtual images because here we are not able to obtain the image of this candle on the screen. So, concave lenses forms virtual, erect and very small images of the object. So, concave lenses forms a small, virtual, erect image of an object. Sign convention for lenses. Children, for lenses we follow sign convention similar to the one used for spherical mirrors. All measurements are taken from the optical centers of the lens. The focal length of a convex lens is positive and that of concave lens is negative. Light rays always falls on the lens from left hand side, means object is always placed at left hand side. Now let's see lens formula and magnification. For lenses, lens formula gives the relationship between object distance u, image distance v and the focal length small f. It is 1 by v minus 1 by u is equals to 1 by f. Magnification. The magnification produced by a lens is defined as the ratio of height of the image h dash and the height of the object h. It is represented by letter m. M is equals to height of the image h dash by height of the object h. M is equals to h dash by h. Magnification produced by a lens is also related to the object distance u and image distance v. It is m is equals to h dash by h is equals to v by u. The negative sign of the magnification and height shows that the image is inverted and real. It is formed below the principal axis, whereas their positive values show that the image formed is virtual and erect. Children, as you know, when we feel some discomfort in reading, doctor advise us to use spectacles. For this, first we go to doctor for checkup and then he advised us to use a lens of specific power. Can you guess what is the meaning of power of lens? Children, the degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. It is represented by letter P. The power of a lens is reciprocal of its focal length. The power P of a lens of focal length small f is given by P is equals to 1 by f. The SI unit of power of a lens is diopter. It is denoted by the letter capital D. 1 diopter is the power of a lens whose focal length is 1 meter. The power of a convex lens is positive and that of a concave lens is negative. Why it is so? Yes, because focal length of convex lens is positive and focal length of concave lens is negative. Dear children, now let's revise the main points of chapter. When light enters obliquely from one medium to another, the direction of propagation in second medium changes. It is called refraction of light. A light ray traveling obliquely from a denser medium to a rarer medium bends away from the normal. A light ray bends towards the normal when it travels obliquely from a rarer to a denser medium. Refraction of light occurs due to change in the speed of light in different mediums. The refractive index of a transparent medium is the ratio of the speed of light in vacuum to that in the medium. Power of a lens is the reciprocal of its focal length. Dear children, now let us discuss some questions. I hope that you know the answers. Question number 1. Which of the lenses would you prefer to use while reading small letters found in a dictionary? Convex lens or concave lens? Yes, the answer is convex lens because it acts as a magnifying lens. Question number 2. When a light ray travels from water into air, where does it bends? Towards the normal or away from the normal? Yes, light ray bends away from the normal because air is rarer than water and light rays bend away from the normal as they move from denser to rarer medium. Question number 3. Which spherical lens is also called diverging lens? Absolutely right. Concave lenses are called